So, hello everyone. I'm really back with my fifth episode of AMR Podcast series, and it is supported by TL Science Communication Certificate Program. And the objective of this podcast is to try to help you out the concepts of antimicrobial resistance in a more simpler way so that you actually understand what's happening in the field. And I'm really delighted to have my guest for this episode, Dr. Andy Edwards. He is working as an associate professor at the Imperial College London, and his work focuses on understanding how antibiotic kills bacteria and how this actually affects by the host environment and the development of novel therapeutic approaches to overcome the current crisis of antimicrobial resistance and tolerance. So without further ado, first of all, thanks, Andy, for accepting my invitation. Great to have you here on this podcast. And maybe I will start with my first question that you are working on colistin resistance. So in the world of medicine, the antibiotics are certain substances, and especially the last drug of resorts, like the antibiotics. There are certain antibiotics that we cannot reuse them, and we are supposed to keep them for future purposes. But do you think are these antibiotics are somewhat doing extra, or are they better than the antibiotics that we currently use?
Yeah, well, thank you for the invitation and the opportunity to talk about, the things that interest me and some of the work that we do. So in terms of last resort, I think we don't want a last resort for anything. We want to have lots of options. And, most of the antibiotics we use, or at least the classes, the types of antibiotics we use, were discovered in the 1940s, 50s, 60s, and so on. And we had lots and lots of different types of antibiotics. And that's really important. If a bacterium acquires resistance to one or two drugs, then we've got plenty more options. And sometimes for really serious infections, we might use those antibiotics in combination just to try and get the most potent effect. So the concept that we even have a last resort is already not a good thing.
Absolutely.
In terms of colistin specifically, it's important to say it's not a last resort because it's the best. We're not saving the best till last. It's a last resort because sometimes it's the only thing that might work. It's actually quite a poor antibiotic. So colistin was discovered in the late 1940s, and it was used in humans for a few years, but then it was almost never used in humans because there were better options. It doesn't work very well. It very often causes kidney toxicity. It accumulates in the kidneys and can damage them. And for a long period, it wasn't used very much in humans at all. It was actually used mostly as a growth promoter in animals. Now, the only sort of good thing you can say about colistin is because it wasn't used in humans, there's not a huge amount of colistin resistance in the bacteria that infect us. So what we've seen in recent years is as bacteria have acquired resistance to most of our frontline drugs, the use of colistin has increased only because it's available, particularly in low-income settings. Because it's been used as a growth promoter, it's quite cheap, it's quite prevalent, and sometimes, as I say, it's the only option. So, yeah, we have to use it.
Yeah. No, thanks for the explanation, because I think it is important for us to understand that it is a tiny bacterium at the end, and now AMR has become a one health problem. So what resistance background, or if a bacterium is resistant to, for example, and which is harbors in the environment, it can also come to a human being, for example, and it can also infect the veterinary livestock. So we all are into this integrated setup kind of thing, and that allows us to, if these drugs are already resistant to these antibiotics, it is really a problem. But do you also see that getting those antibiotic not in use in the clinic also has some other plans? For example, certain industry, they don't want to deploy these antibiotics, and also they don't see the profit to actually invest much amount in antibiotic discovery, because it's a risky business for them. Because even though if you produce a new antibiotic, you may not sell it right away because you have a strict restriction of putting that out of your shelf, because you know that this is something that you may use for later purposes if it is needed. So how we could palliate or try to like trigger the developmental pipelines?
Yeah, I think that's a really critical point, and it's one of the most important points, because on the one hand, you've got increasing prevalence of multi-drug resistant organisms. On the other hand, you've got an almost total lack of new drugs entering the market. So it's very much a perfect storm. If you look at the drugs that have been successful, they tend to be drugs that can be used by as many people as possible. The sort of so-called fat-busting drugs, drugs used to treat cancer or cardiovascular disease. Those drugs can be given to as many people as humanly possible, as many people that can afford them, without any real concerns. Antimicrobial resistance, by which I mean not just bacteria, but viruses and protozoan parasites, it's very different. This concept of resistance is a real problem. So we have to restrict the use of these drugs, and that massively disrupts the economic model. So I think there are only really two things that are going to shift the dial on this. One, and we're starting to see this, is governments stepping in and filling the void and saying, we will buy this as a social good. The other is if drug resistance gets so bad that it really starts to impact lots of other areas of medicine. The drugs we use for cancer treatment rely on the availability of safe and effective antibiotics. As the needle moves on that, drug companies will have to start developing antibiotics to accompany their other treatments. But fundamentally, this isn't about pointing fingers at drug companies, because lots and lots of companies have tried it and they've gone bust in the process.
I see.
So they have an obligation to their shareholders and their employees, of course. So it's a very difficult balance, and I think ultimately, because antibiotics are in a special class of their own, it's going to come down to governmental funding. And there are a few different models being employed at the moment, and I don't think we necessarily know which one's best. But that's the only way I see of that void being filled in the short term.
But maybe talking about the models. So even though if you see sometimes that some antibiotics that you recently developed, they are working like a superhero in a lab, and they're like trying to almost kill many amount of bacteria. But it could happen that when you actually try to integrate that into a host environment, it may not work in a way that you would have expected. So do you think it's a problem that we still do not understand, that how a particular antibiotic may work in a human being or in a host model, and what can actually complicate those things? So what are the criteria that we may actually want to look upon?
Yeah, so almost all early stage antibacterial work focuses on using bacteria that are rapidly growing under sort of rich laboratory conditions. And that's completely understandable. If you're doing a high throughput screen, you don't want to complicate things. Things are already quite difficult.
Yes.
And then as you progress those compounds into host conditions, you can see either host toxicity arising as a concern.
Yeah.
But also the physiology of the bacteria changes. And usually bacteria in the host aren't growing as quickly. They might be living within host cells. They might be stressed in ways that actually reduce their susceptibility to antibiotics. But also in some cases, so azithromycin, for example, that seems to work better under host conditions than it does in the lab. So I think, we don't really know many of the ways by which these changes occur in the host, but something that we do try and do is incorporate at least some basic models of the host environment to understand this. I'm actually involved in 3 projects that are looking at this a bit more in gram negative. So one of them's led by Jess Blair at the University of Birmingham. That's understanding how the host environment modulates the gram negative cell envelope, and that in turn affects antibiotics getting into the cell.
Nice.
And then we've got a couple of other projects where we're working with chemists. So one of these is sponsored by GSK and the Fleming Initiative, and the other by Gradi, which is Gates, Wellcome, and Novo Nordisk Foundation. And the idea there is to understand the chemical properties that influence antibiotics getting into a cell. And of course, those chemical properties can be affected by the host environment. And so, by starting to bring in a few host relevant factors, what we hope is that we can then de-risk subsequent development. What you don't want is to find something that's really cool in the lab, take it into an animal model or a human, and then find that it doesn't work, because that's very costly.
Absolutely. Yeah. So I also saw, once I was going through your profile, that you have worked on virulence aspect of a particular pathogenic bacteria. And I personally did my PhD on resistance versus virulence trade-off. So I used Pseudomonas aeruginosa as a model, and I wanted to see when a bacterium like Pseudomonas, it's a pathogenic in nature, and when you actually allow them to evolve antibiotic resistance, is it also trying to compromise on its virulence? And I saw it is totally dependent on what kind of antibiotic that has driven resistance. So I also saw the recently authored paper by Lamy et al. Published in Infection Immunity, which also nicely demonstrated the fact that a bacterium changes its biology to become more resistant to an antibiotic. It's like, putting on a heavy exposure, expensive armor at a cost of virulency, for example. But then one could argue that if it is really happening, then evolution of resistance is not a problem anymore, because let them evolve, because they are also becoming less virulent anyhow. But then how do you think, but still we can actually think that the both resistance and virulence are increasing. So where exactly are we going wrong? Or can we not really expect to see such an ideal environment that we usually try to see in a laboratory condition?
Yeah, so I mean, as you say, it's very context dependent. Generally, we would expect there to be a cost of resistance. Not always the case, and there are some things, and we know efflux pumps, for example, can contribute to both resistance and to virulence. But broadly speaking, yeah, we might often see that resistance comes at a price. As you say, like putting on heavy armor reduces your mobility. So cost benefit. I think the key thing is that when we think about the most drug resistant pathogens, we tend to see them in environments where lots of antibiotics are used. So if you take a hospital, whether that's in a low income setting or a high income setting, generally the further you get from an inpatient setting through to intensive care, you'll see more antibiotic use and you'll see more drug resistance.
I see.
So, but the people who are getting these multi-drug resistant infections, for the most part, have some other situation or condition that means their immune system is compromised. So we know most bacterial infections occur either in the very young or the very old. People with a chronic illness, someone with diabetes, essentially something where their barriers are disrupted, let's say a surgical wound infection or trauma, or their immune system is compromised with diabetes or being very young or very old. So to cause infection in those people, the bacterium doesn't have to work so hard. It doesn't have to be so virulent. A knight in heavy armor can easily kill an old person. That's no problem. They're often not causing infections in the sort of young and fit, although it does happen sometimes. But what is crucial for those infections in those hospital settings, particularly, is being drug resistant. So evolution is never, ever about the perfect, scenario being best at everything. It's about being best equipped for the particular situation that the organism finds itself in. So an organism that causes infection in healthy people in the community is probably less drug resistant and more virulent, whereas in the hospital, it tends to be a bit more drug resistant and less virulent. That's not a universally true statement, but broadly, I think it explains how context can be very important and how organisms need to balance virulence and resistance, as well as a bunch of other factors, of course.
Yeah, I actually recently submitted my paper, and also it was about three different antibiotics I used: ciprofloxacin, piperacillin tazobactam, and streptomycin. So, as you already have noticed, that these three antibiotics are from three different classes, and I observed three different results for three different classes. To be even like just to give you an overview, so I found that in ciprofloxacin, none of the Pseudomonas aeruginosa produces pyocyanin at all. So it's just they are not at all producing pyocyanin. So obviously, we also tried to dig deeper into the mutational landscape, and we found that they have a mutation, and that actually allows them to, disrupt the codon sensing circuits, and that actually allows them to throw out the precursor molecule that the bacterium would need to actually produce pyocyanin, because they have a highly active or superactive efflux systems, and this efflux systems are actually throwing out the precursor molecule for PQS codon sensing system that it has. But I'm not going in much detail. Maybe I can share the preprint with you. So yeah, and like afterwards. So yeah, but that's a really quite fascinating that I actually came to. And maybe the last question before I actually conclude today's session is that when you look at the current AMR crisis, in your opinion, what is the single greatest discovery or the breakthrough that we are still awaiting in the field of AMR? And looking at the global stage, the world has recently witnessed corona pandemic. So this COVID pandemic has actually allowed us to learn lessons. But do you think, are we better prepared for the silent pandemic that is going to happen in the next 25 years, per se? I'm sorry, I think you were in mute, Andy. Sorry, Andy, I think you were in mute.
Right. Yeah, well, first of all, congratulations on getting the paper out. The last mile of writing a paper is always the hardest. You know, it's always good to get it out there and share it. And I'm a big fan of preprinting as well. In terms of what do we need, we talked about the economic situation. I think, and I am biased here, but I with my focus at the moment on gram negatives, I think understanding what enables small molecules to get into gram negatives and then to stay there is really important. I think if we can, you know, a lot of small molecules work either against a specific target in a target-based screen, or they work against strains with, you know, like a Toll-C defective strain where it can't pump the small molecule out. If we can learn the right chemical space to be doing our screens in the right space that we know will help those small molecules get into bacteria, that I think is technically probably the most important thing we could be doing right now. But as I say, I'm biased because that's what I work on with a lot of my colleagues here at Imperial and elsewhere. In terms of the pandemic, I think it's really interesting. I think on the one hand, it shows what can happen quickly.
Yes.
With appropriate support, coordination, cooperation. We saw, you know, some exceptionally good vaccines produced very quickly. And I think there's a lot of potential there for more vaccines to be deployed in combating bacterial pathogens. And colleagues here I know are particularly keen on targeting things like Klebsiella. So there's a lot of potential there. I think with AMR, it's a little bit like climate change in that there's no one solution. You know, the work we do is focused more around new antibiotics, but of course, having better diagnostics and knowing when to use and how to use our drugs more appropriately. Because, you know, we talked about last resort drugs earlier on. There might be situations where we want to use those drugs early in treatment, not late when the infection's more established. So having better diagnostics is useful. More surveillance to understand what's going on. Sanitation, of course, is really important. We see outbreaks of disease in you know, for example, in the US at the moment, there are outbreaks of infection that better sanitation could have prevented, and then we don't even need to worry about, you know, treatment. But I think we also need to be aware that the COVID pandemic led to some negative outcomes, some entrenching of views around vaccines, or, you know, what we might term conspiracy theories. We whilst we might disagree with them, we need to recognize them. And I think understanding how the population engage with the information, how they adhered to the requests and public perception of things, I think is really important. I think there are a lot of lessons to be learned, ranging right from the science, but through to global public policy, I think is really important. So there's a lot to learn there. I think people are familiar with AMR. I think they are aware of the risks of it. Now it's about getting the message out about what people can do to make their important contributions. Because ultimately, we all need antibiotics. We all use antibiotics. So again, coming back to the climate change analogy, there's always something that each and every one of us can do.
Absolutely. I think that is going to be really important for us to identify the different layers of AMR. And I think we were really aware of the crisis now, and all we need to do is just try to disentangle each of the part and try to focus on their own aspects. And I'm optimistic that we may try to be in a better place, and perhaps the pandemic that we are going to we may actually have the weaponries to stop. So I think with that, at the end of our conversation, I would actually really like to say thanks from the bottom of my heart for sharing your time and also just discussing this with me. It really helps me a lot. It helps my audience a lot to learn about the concepts. And yeah, with that, I would really like to say thanks for your time. So yeah, thank you very much.
Thank you for the invitation.
Yep.
Great to talk about the work. Thank you.
Thank you.